deep within our oceans, move a network of elusive, unseen global currents. Currents that hold the astonishing ability to reshape life on Earth as we understand it. They remain tightly interconnected, working in unison like vast conveyor belts that shift oxygen, warmth, salt, nutrients, and life itself smoothly and tirelessly across our blue world. They serve as the quiet guardians of Earth's climate, the essential systems that so often fade into the background of climate discussions. That is, until something begins to fail. Perhaps the most powerful of these great ocean engines is the AMOC, the Atlantic Meridional Overturning Circulation, a cornerstone of the planet's climate machinery, and one that scientists warn is not only declining, but may even face collapse as early as 2026. Although such collapses have occurred before, nothing like it has happened for almost 10,000 years. And this time, one crucial factor has changed. We are here. How could something so profoundly consequential slip past us without clear recognition? If the unthinkable were to unfold, what would it mean for life on Earth? I'm Collins Klintz, and you're watching Stellar Earth. Join me in this video as we uncover what is unfolding beneath the surface. Okay, that's quite a lot to take in, isn't it? This is the world we find ourselves in, 2026. Yet considering that an AMOC collapse inspired the 2004 film The Day After Tomorrow, it hardly feels like something that could be looming so close, does it? There seems to be little discussion and even less urgency surrounding this issue. In fact, many people have never even heard of the AMOC. Perhaps that's one of the major challenges with a force that can neither be seen nor directly measured. Because the truth is, signs of a weakening AMOC have been appearing for the past 60 or 70 years as our planet has steadily warmed. And some researchers have pushed further, arguing the AMOC has declined by at least 15% since 1950. And is now at its weakest level in more than 1,000 years. The clearest hint? A strange cold patch that has appeared across the North Atlantic. Strangely, this region is the only place on the planet that has cooled during the past 2 decades, while nearly everywhere else has continued to warm. Any guesses why this might be happening? Yes, it's tied to the AMOC slowing down. One of the AMOC's central roles is transporting heat. It functions as one of Earth's largest engines for moving warmth, carrying the equivalent of 50 times the energy humanity consumes. The same amount of power flowing through 1 million power stations operating at once. So when the system loses strength, this part of the ocean becomes colder. Since 2021, the consensus within the Intergovernmental Panel on Climate Change, IPCC, was that the chance of crossing a collapse threshold this century was below 10%, with medium confidence. But by October 2024, 44 climate scientists from 15 nations released an open letter to the Nordic Council of Ministers, warning that the danger of an AMOC collapse has been significantly underestimated and is likely higher than previously believed. A slowing AMOC means this region grows colder. Since 2021, the prevailing view within the Intergovernmental Panel on Climate Change, IPCC, was that the likelihood of crossing a collapse threshold before the century's end sat below 10%, supported by only medium confidence. But as recently as October 2024, a coalition of 44 climate scientists from 15 countries sent an open letter to the Nordic Council of Ministers, arguing that the danger of an AMOC collapse has so far been seriously understated and may be far greater than earlier assessments suggested. A new study, published in Nature Communications, drew on sea surface temperature records extending back to 1870 as a proxy for evaluating how AMOC strength has changed through time,
ultimately estimating that the circulation could collapse any time between 2026 and 2095. So which analysis is correct? It seemed time to find some real answers. So let's descend into the AMOC itself. What it is, how it functions, and why it matters. A good place to begin when diagnosing why something is failing is to understand what that something truly is in the first place. What does this mysterious, unseen giant, capable of reshaping life as we know it, actually do? It's easy to forget that Earth's oceans are all connected, a single vast body of water linking every continent, every hemisphere, every shore. And the AMOC plays a key role in keeping those oceans unified, functioning almost like an enormous planetary mixing bowl. It moves water, heat, nutrients, dissolved gases, and microscopic life across the globe through its flowing currents. The AMOC is a beautifully complex network of ocean streams and swirling eddies, those circular spirals of moving water. It forms a remarkable vertical loop stretching the full length of the Atlantic Ocean, and if you mapped it, the pattern would resemble a massive strand of spaghetti draped across the world. And these currents are especially intriguing because several distinct types exist within this system. Those last currents are the ones that matter most here. They include the slow-moving flows that extend from the surface all the way to the sea floor, driven by shifts in saltiness and temperature. This process is known as thermohaline circulation. Thermo referring to temperature, and haline referring to salinity. The AMOC is a crucial branch of this global thermohaline conveyor belt, carrying water from north to south and back again in an immense looping cycle within the Atlantic Basin. It pushes warm surface water northward and returns cold, dense water southward at depth. Through this motion, it distributes heat and nutrients toward higher latitudes and transfers carbon into the deep ocean, where it can remain for centuries. Things begin off the eastern coast of North America, where the Gulf Stream, a component of the AMOC, transports warm water from the Florida Straits up toward the Grand Banks near Newfoundland. From there, the North Atlantic Current sweeps this water toward Europe and the Norwegian Sea. And when this warmer water reaches the colder subpolar regions near Greenland or the Arctic, it cools, grows denser, and begins the long descent that drives the overturning loop. Every second, this circulation moves an astonishing 17 million cubic meters of water northward, roughly equal to 7,000 Olympic-sized swimming pools. In doing so, it transports around 1.2 petawatts of heat, a figure 100 times greater than the total energy humanity generates from every power source combined. And all of it is vital for balancing Earth's climate. As remarkable as this is, the motion itself happens surprisingly slowly, which feels almost counterintuitive for such a powerful planetary system. In fact, the AMOC's full circuit is incredibly sluggish. A single parcel of water takes close to 1,000 years to complete the journey along this immense conveyor, and it can't afford to slow much further. Yet that is precisely where the problem lies. Before we continue, it's worth clearing up a common confusion between the AMOC and the Gulf Stream. As mentioned earlier, the Gulf Stream is just one component of the broader AMOC, not the entire system itself. It's like a vital internal organ. The AMOC would not function properly without it. The Gulf Stream begins at the tip of Florida. It's a warm, fast-moving Atlantic current that follows the eastern coastline of the United States and Canada before sweeping across the ocean toward Europe. Its role is to keep Western Europe far warmer than its latitude would naturally allow. For instance, where I'm standing today sits roughly level with the cold zones of Canada, yet here in England, we enjoy a much milder climate. Without the Gulf Stream's steady flow of warm water, the UK would be several degrees colder. Not quite the day after tomorrow scenario, but easily 3 to 4 degrees Celsius lower. And mainland Europe could be reduced by 10 degrees or more. It acts like a rapid highway, a major stretch of the route taken by warm water traveling from the South Atlantic into the far north. When that highway ends, the remaining warm water follows narrower pathways as it continues its journey northward. As it moves through the Atlantic, it gradually loses heat through evaporation, leaving behind cooler, saltier water that eventually meets the fresher waters of the North Atlantic. The Gulf Stream is driven by a vast system of rotating currents and strong winds, known collectively as an oceanic gyre. Earth has 5 of these gyres: the North Atlantic, South Atlantic, North Pacific, South Pacific, and Indian Ocean gyres. Because of its location, the Gulf Stream forms part of the North Atlantic gyre. Now that we've untangled the currents, let's shift our focus back to the AMOC, and more specifically, to the influence climate change is already having on it. As we noted earlier, everything on Earth is interconnected, and the same principle applies here. Remember that strange cold anomaly we mentioned earlier? The lone region on Earth that has cooled over the past 20 years. That chill doesn't just sit at the surface. It extends more than 2,000 meters deep, and it stands as the clearest signal of a slowing AMOC. Along with cooling, salinity in this region has also dropped, falling to its lowest level since measurements began over a century ago. This matters enormously because fresher water is far less dense, making it increasingly difficult for it to sink and join the deep, colder return flow we described earlier. One major explanation scientists believe is the surge of fresh water melting from ice as greenhouse gas emissions continue to rise. At least 2 studies examining advanced climate models and observations have shown that the North Atlantic warming hole is largely human-driven, caused by reduced northward heat transport linked directly to greenhouse gas emissions. To understand how much of this decline is human-caused, we look to the past. Before widespread temperature measurements existed, scientists turned to proxy data, the lingering traces of past climates stored in slowly accumulating natural archives like seafloor sediments and ancient ice. Clues such as the ratio of oxygen isotopes locked within the microscopic shells that form deep ocean sediments reveal past surface temperatures. The size of sediment grains on the sea floor shows how strong currents once flowed above them, helping reconstruct historic ocean conditions. All of these records point toward a long-term weakening of the AMOC beginning in the early to mid-20th century. Climate models have long predicted that warming would weaken the AMOC, and the underlying physics is well understood. Paleoclimate evidence strongly supports this, showing that the AMOC's decline closely matches the timeline of unprecedented modern global warming. In short, human activity has almost certainly heightened the conditions that push the AMOC toward instability.
We can see several shifts occurring now. Greenhouse gas emissions have risen sharply, and Arctic amplification is accelerating warming in the high north. The global water cycle is intensifying as well, driven by extra energy entering the system from the sun, creating more extreme swings between floods and droughts. There is increased evaporation in the subtropics and greater precipitation in higher latitudes. And all of this is happening even before we mention the melting of sea ice. Here comes the major factor. The Greenland ice sheet is losing around 270 billion tons of ice
every year. Fresh water that makes the surrounding ocean progressively less salty. This dilution weakens the density of surface waters, triggering what scientists call salt advection feedback, a positive feedback loop that directly influences the AMOC's strength and acts as a tipping mechanism that can push the system toward a slowdown or collapse. In 1961, U.S. oceanographer Henry Stommel recognized that the salinity of Atlantic waters could drive the AMOC toward a tipping point. In essence, the AMOC flows because the North Atlantic is salty, and it stays salty because the AMOC flows. It's a chicken and egg problem, or in scientific terms, a self-reinforcing feedback cycle. And the reverse is also true. If the North Atlantic becomes less salty due to increased freshwater, the water becomes less dense, and the AMOC slows. That slowdown brings even less salt back into the region, weakening the AMOC further. This looping instability sets the stage for one of the most fascinating and troubling patterns in Earth's climate system.
One of the most intriguing aspects of this vast, interlinked ocean engine is its long history of instability. In other words, the AMOC has collapsed before, and when it did, the results were tied to some of the most extreme climate episodes in Earth's recent past. It's easy to forget that we are still living within an ice age. An interglacial phase, yes, but an ice age nonetheless. And during the last glacial period, the climate was anything but steady. To understand earlier AMOC behavior, we look at some dramatic climate swings that unfolded within the past 100,000 years. Recent, at least from a paleoclimate perspective. From these ancient records, we know that some of the most abrupt and spectacular temperature jumps, known as Dansgaard-Oeschger events, or DO events, were likely triggered by instability in the AMOC. These events, marked by rapid warming followed by slower cooling, punctuated much of the last ice age. This graph shows reconstructed temperatures from ocean sediments and ice core over the past 60,000 years. The green curve represents sediment data, while the blue curve shows ice core records. What's striking is that when those blue and green lines plunge sharply downward, they align with Heinrich events, marked in red, as well as the numbered DO events. This alignment suggests that an unstable AMOC likely drove these dramatic climate spikes. During the Younger Dryas, a period of sudden and intense climate disruption, the AMOC slowed dramatically around 12,500 years ago, plunging the northern hemisphere back toward near-glacial conditions. This slowdown was triggered by meltwater flowing from the Laurentide ice sheet, which unleashed massive surges of icebergs into the North Atlantic, the very Heinrich events recorded in Earth's sediments. We can see traces of these ancient episodes preserved in the ocean floor. Distinct layers filled with coarse-grained material carried from land spread across vast stretches of the North Atlantic. These layers testify to both the explosion of icebergs from North America and the expansion of cold polar waters. Scientists believe these massive freshwater floods reduced ocean salinity enough to weaken deep water formation, and with it, the AMOC itself. Because the thermohalion circulation is central to carrying heat northward, a slowdown would have caused the North Atlantic to cool dramatically. Later, as the influx of fresh water diminished, salinity increased again, deep water formation strengthened, and the climate gradually recovered. These coarse sediment layers, spread across huge regions of the North Atlantic, give us clear evidence of both the surges of icebergs released from the Laurentide ice sheet and a southward push of cold polar waters. They are a geological fingerprint
of how sensitive the AMOC has always been to changes in freshwater and climate. To put the Younger Dryas in perspective, this abrupt cooling event nearly reset the northern hemisphere back to glacial conditions. It was triggered by meltwater pulses flooding into the Atlantic, shutting down the AMOC almost entirely. Only when the freshwater input slowed did the system regain strength and the climate return to a warmer state. These dramatic shifts remind us that the AMOC has a long history of rapid change, and that when it falters, Earth's climate responds quickly and profoundly. All right, so by now you've probably grasped the scale of this vast and very real problem, which brings us to the central question. When might the AMOC collapse? Notice the emphasis on when, because the thing that struck me most while researching this topic is that scientific studies offer a wide range of predictions, and yet nearly all of them agree on one point. If we continue along our current path, the issue is no longer if, but indeed when the collapse will occur. As mentioned at the beginning of this video, until only a few years ago, the prevailing view within the Intergovernmental Panel on Climate Change, IPCC, was that the probability of crossing a collapse threshold this century was below 10%, with only medium confidence supporting that estimate. The most recent 6th IPCC assessment found that even under a low emissions pathway, the AMOC is projected to weaken somewhere between 4 and 46% by 2100, depending on the model used. Under a high emission scenario, that range increases to 17 to 55%. But newer studies now suggest the possibility of a collapse as early as 2026. So what exactly is happening here? Who is correct and who is mistaken? It's a valid question, but the answer is far more complicated than a simple right or wrong. Much of the uncertainty stems from how the AMOC is modeled and the assumptions and physical processes each model incorporates. A major limitation is that, beyond paleoclimate records, we simply haven't been measuring the AMOC long enough to produce an observational record robust enough for absolute certainty. The IPCC relied heavily on a system called CMIP6, which blends results from roughly 100 different climate models produced by 49 research groups around the world. Critics argue that the AMOC represented within these models was too stable, meaning it was tuned, much like adjusting a car engine, to behave more reliably than reality might suggest. This tuning could have made the models underestimate how vulnerable the AMOC truly is. On the opposite end of the spectrum are studies claiming a collapse between 2026 and 2095 with up to 95% confidence. How did they reach such early dates? These researchers relied on a different approach called reanalysis, attempting to overcome the short observational record by using sea surface temperature data from the North Atlantic subpolar gyre. But SST as an indicator of AMOC collapse remains heavily debated in the scientific community. Actual AMOC measurements since 2004 have already disproven the 5 ship-based data points used in those more alarming papers, measurements taken several years apart that paint a misleading picture of long-term decline. To their credit, the authors acknowledge significant uncertainty in their own conclusions. Returning to our central question, when might the AMOC collapse? The study using SSTs estimates a central collapse year of 2057, a figure echoed by another paper predicting a collapse between 2037 and 2064, 10 to 90% CI, with a mean of 2050. You can decide for yourself which range you find most credible, but one thing does seem increasingly clear. If global warming continues unchecked, many of us alive today may witness something extraordinary and extraordinarily dangerous. You're free to draw your own conclusions about the exact year, but one thing feels increasingly undeniable. If we continue warming the planet at our current pace, something profound is likely to unfold within many of our lifetimes. A full AMOC collapse would be a planetary-scale crisis, and there's no gentle way to frame it. So, if this system were to fail, what would it mean for the rest of us? Europe would be among the first to feel the shock. Major European cities could see temperatures drop between 3 and 10 degrees Celsius within a few decades. And in some regions, the impact may be even harsher. February temperatures in Bergen, Norway, for example, could plunge by 35 degrees Celsius over a century. This wouldn't create a new ice age overnight, but the North Atlantic and Europe would cool dramatically, with England, Scotland, and Ireland resembling the climate of northern Canada. Winter storms across Europe would surge in frequency and intensity, and Western Europe would receive far less rainfall, with huge repercussions for agriculture in places like France and the UK. Farming would become more like trying to grow crops in northern Norway. But Europe wouldn't be the only region affected. Atlantic sea levels could rise by as much as 70 centimeters, swallowing coastal areas around the world, rendering some densely populated regions uninhabitable. Scientists also predict that the tropical rain belt would shift southward, a devastating change, as rainfall would move away from rainforests towards regions unaccustomed to such heavy moisture. This means drought in some locations and catastrophic flooding in others. Rainfall patterns in the Amazon would change sharply, drying the Sahel and weakening Asia's summer monsoon. As the northern hemisphere cools, the southern hemisphere would warm even more, because heat that would normally travel north would instead accumulate in the tropics, driving dramatic temperature spikes. A collapsing AMOC would also reduce the ocean's ability to absorb CO2 from the atmosphere. This matters because sinking water in the North Atlantic locks away immense amounts of carbon in the deep ocean. With less of that downward transport, far more CO2 would remain in the air, the very last thing our climate needs right now. And while some might argue that cooler conditions in parts of the world could balance out some warming, the truth is stark. There is no region that benefits. Climate averages don't tell the real story. Weather does. Scandinavia and Britain cooling, while Spain and Italy warm, would intensify contrasts, fueling severe storms, greater variability, and extreme weather beyond anything we've experienced. You get the picture.
Some researchers have suggested that an AMOC collapse might temporarily delay certain stresses already threatening the Amazon, at least when combined with the effects of global warming. In the earliest stages of a slowdown, cooler temperatures and increased rainfall in the Amazon could ease some of the heat-driven pressures on rainforest vegetation, slowing the shift toward a savanna-like ecosystem. But this relief would be short-lived and depends entirely on the timing between an AMOC collapse and the trajectory of global warming. If global temperatures rise beyond a critical threshold before such a collapse occurs, the Amazon could transition irreversibly into a drier, more open landscape. Because the AMOC influences rainfall patterns so strongly, its weakening, or collapse, could also disrupt the Amazon's seasons. The dry season could become the wet season, and the wet season could turn dry. Reversals that would place enormous strain on the rainforest's intricate ecological balance. These shifts would ripple outward, affecting everything from biodiversity to carbon storage to regional weather systems. The Amazon is often called the lungs of the planet, but it also acts as a massive atmospheric engine, and destabilizing it adds yet another layer of risk to an already vulnerable climate system. In short, while a weakening AMOC might provide brief, localized benefits in the Amazon, these would be fleeting. The long-term consequences would be far more disruptive for both the rainforest and the planet it supports.
The AMOC is clearly something we must watch with extraordinary care. But how do we actually do that? How do we track the changes within this vast, shifting system and monitor how quickly or how far its slowdown is progressing? Scientists measure the AMOC using instruments deployed across multiple latitudes in both the North and South Atlantic. The UK's National Oceanography Centre leads two major monitoring programs, Rapid Climate Change, and OSNAP, Overturning in the Subpolar North Atlantic. Both networks rely on moorings, cables stretching hundreds to thousands of meters down, equipped with sensors that track current speed, temperature, salinity, and the direction of water flowing across the arrays. One of the most important signals to watch when assessing whether a collapse may be approaching, the alarm bell in a sense, is the strength of the Atlantic flow measured by RAPID since 2004. Other observations help track winter mixing in the northern Atlantic and Nordic seas. If deep mixing declines significantly, that could indicate we are nearing a critical tipping point. There are early signs, as we've shown, but the dataset is still too limited to say when such a threshold might be crossed. This brings us to the final question. The AMOC has collapsed before. Could it recover again? Well, possibly. If the AMOC were to collapse, even if freshwater input later reduced to present-day levels, the system might remain in its collapsed state. This inability to return to its original configuration after the driving force is removed is known as hysteresis. Modeling by the UK Met Office indicates a brief window of resilience might exist after the AMOC crosses a threshold, a period during which the system could recover if freshwater flow were cut off quickly enough. In one experiment, the AMOC recovered if freshwater stopped after 20 years, but not if it stopped after 50. This gives a resilience range of roughly 20 to 50 years. But that window shrinks if the freshwater influx increases at a faster rate. The last recovery took roughly 1,000 years, but that was under conditions very different from today. CO2 levels are now higher than at any point in 15 million years, and we are still, technically, in an ice age. Based on everything I've read and everything we've explored, it's difficult to avoid the conclusion that if we continue as we are, a significant slowdown or even a collapse is likely within many of our lifetimes. A collapse in 2026 can almost certainly be ruled out based on the unreliable data behind that claim. Likewise, the IPCC's end-of-century estimate now appears too optimistic. The timeframe that emerges most consistently is the 2050s. Preventing this outcome comes down to the same simple truth you may already know. We must dramatically reduce the rate at which our planet is warming. It sounds straightforward, and yet the scale feels overwhelming. When we think of climate change, we often think of what we can see: droughts, rising heat, extreme weather, floods, melting ice. But rarely do we think about what remains invisible, the underlying forces, the hidden engines like the AMOC that quietly shape life on Earth. Our planet has demonstrated resilience across countless extreme events in its history. It always finds a way to respond, and it would do so again if or when the AMOC collapses. But while Earth itself would endure, whether humanity would, or whether billions of people's current way of life would, is a far more consequential question. The AMOC shows us just how delicate and interconnected Earth's systems truly are. It is as awe-inspiring as it is dangerous, and like so many other vital components of our world, it now sits at the top of the list of things we must urgently protect. Astrum Earth exists to make this remarkable planet clear, accessible, and deeply relevant to you. We aim to show a side of Earth you may never have seen, combining rigorous research, thorough analysis, and storytelling that brings the science alive, all through an audio-visual experience you'll remember. Thank you for watching, and we'll see you in the next one.